Morning, everybody. Today we're going to talk about matter and measurement, and particularly how measurement and sig figs work together. So let's start the lesson. So what is the nature of measurement? Measurement basically has two parts, quantitative observation as well as the unit. So there is basically the number, how long, 20 feet, 30, 15 meters, and of course the scale or the unit. And both of those combined are a very important part of measurements. So example would be 20 grams. There would be 6.63 times 10 to the negative 34 joule seconds. And so when looking at these examples, just keep in mind that your grams, units, are just units. So when you compare it to kilograms, compare it to micrograms, it's going to be important to pay attention to how that changes the number when we convert later. So the fundamental SI units, or Le Système International, there are 7 basic units that are out there. We have mass, length, time, temperature, electric current, amount of substance, and luminous intensity. These are all what we call the most fundamental units. And the units for the SI units, kilograms is mass, meters is length, seconds is time, Kelvin is temperature, ampere is current, mole is for substance, and candela is for luminous intensity. And for the most part, we deal with kilogram, we deal with meter, we deal with seconds, we deal with Kelvin, which we'll learn about, as well as mole. Ampere we will learn as well, but candela we really don't use. That's mostly for AP Physics, actually. And the abbreviations for each of these will be kg, meters, seconds, K for Kelvin, A for ampere, MOL for mole, and CD for candela. For the most part, try to remember all these, except for candela. And it just gets complicated from here. From a kilogram, you can have this most basic fundamental unit be part of other units. Newtons of force, pressure, absorbed dose, dose equivalent. Energy has kilograms as well. Watts has kilograms. And when you talk about meter or length, that's in volume, area, velocity, acceleration. So these are the fundamental units, and when you combine them, you create other units that are out there that are derived, okay, with special symbols and special names. And we'll get through each of these as we deal with them in the class. Now, what are the SI prefixes that are common to chemistry? Some of you have seen this in the assignment already. There's a huge range of prefixes, and the purpose of prefixes is to make it actually easier for the scientist. Most scientists in general are lazy, and so if they can find a way to create a symbol, then they're going to actually do that. And so mega, kilo, deci, centi, milli, micro, nano, and pico are some of the prefixes that are out there, and these are the ones that typically show up on the AP exam. So you want to make sure you memorize every single one of these prefixes and what the number means. And so mega symbol is a capital M, kilo is a K, deci is a D, centi is a lowercase c, milli is a lowercase m, so mega is capital, milli is lowercase, micro looks like a U with a tail on it, and it's really just a very fancy looking M. N is nano, and P is pico. And of course they have number representatives. Mega in general means 1 million, and so 10 to the 6 is the exponent for that. Kilo is for 1,000, so 10 to the 3rd. Deci means 1/10, or 10 to the minus 1. Centi is 1/100th, so it's 10 to the minus 2. Milli is 1/1000th, so it's 10 to the minus 3. Micro is 1/1,000,000th, so that's actually a lot smaller. And nano, I'm not even going to write out, it's 1/1,000,000,000th, and pico is 1/1,000,000,000,000th. And so these all represent very small numbers, and because it's chemistry, we deal with a lot of small numbers. And so these come in handy in chemistry, And these, of course, the bigger numbers. Once we get past 10 to the 6, we typically don't use prefixes for us. Not that you can't. There's giga after mega. There's tera after that. And everything increases by a factor of 1,000. So just keep that in mind as we move on. But make sure you work on memorizing these particular prefixes. You are expected to know these prefixes for the AP exam. So in terms of measurements, so when we measure, this is where all these numbers come into play and all of these units come into play. Uncertainty is a big portion of what we deal with in chemistry. And a digit that must be estimated is called the uncertain digit in the measurement. And a measurement always has some degree of uncertainty to deal with. And so when we deal with measuring, when you say something is 12 feet, there's really some kind of uncertainty in there when you communicate that number to me. When you say something is 12 feet 3 inches, there's a different level of uncertainty compared to 12 feet because of the fact that you've indicated that you are capable of measuring to the inches level. Now if you say 12 feet 3 inches and a quarter, now you're even giving me another level of uncertainty, which says that you're actually more accurate with that one compared to the very first one. And so you want to make sure that you understand that anytime you measure, you want to try and go as far as you can in terms of accuracy given the measuring device. So measurements, of course, are performed with instruments, and no instrument can read to infinite number of decimal places. And because of this, every measurement out there has uncertainty. And whenever you measure, you're going to deal with precision and accuracy. Well, accuracy refers to the agreement of a particular value to the true value. In all cases, we want to be as accurate as possible. Okay? On the other hand, precision refers to the degree of agreement among several measurements made in the same manner. And so if you measure something 3 times and you get 3 different values, then you are not agreeing among your several measurements. And so it's going to be important that you find a way to make sure not only you are accurate, but whenever you measure, you're also precise, meaning that all of your measurements are always agreeing with each other. And that's one way to check for accuracy. Now there's 3 possible scenarios here that you can have. You could be neither accurate nor precise. So in this picture over here, you can see that these 3 arrows are not hitting the target. So they are neither accurate nor precise because they're not even hitting the same level of colors on this target. On the other hand, you have this one where it's precise because you have agreement between all of these guys, but it's not accurate because it's not hitting the actual center of the target. Last but not least, you could be both precise and accurate, and of course the goal in chemistry is to be both precise and accurate. And when we deal with error, there's of course different types of error in chemistry. First one is random error, which is called indeterminate error. It has a measurement, has an equal chance of or probability of being high or low. And whenever you deal with error in my class, it is best to always deal with what is called random error. And the idea is that you could possibly high, you could possibly be low, and you are not doing something to cause the error. It is just part of the system that you are dealing with. Systematic error, on the other hand, is what we call determinate error. It occurs in the same direction each time, high or low, often resulting from poor technique or incorrect calibration. This can result in measurements that are precise but not accurate. And of course, our goal is to make sure that you do not deal with what is called systematic error, because you are probably making that error all the time. You are reading the instrument incorrectly all the time, and as a consequence, you're going to get a specific value. And so with all these errors, of course, whenever you get a measurement, you have to deal with what is called numbers. Your numbers basically communicate to me the level of accuracy in your measurements. And that is where we get into the rules for counting sig figs. And I will cover this in the next video